Alright, here we have the notes for section 1-2, which deals with linear measure and precision. So here are our main ideas: measure segments and determine accuracy, and then compute with measures, and then your vocab words there on the right. So first thing here, so unlike a line segment, which sometimes just called the segment, can be measured because it has two endpoints. So a line goes on forever. You cannot measure its length. A line segment, though, is just a section, a segment, so you can measure it. So a segment has endpoints A and B. It can be named either A, B, or BA. So if you notice, the symbol up above here does not have the arrowheads at the end. We say segment ends, so you do not put the arrowheads on it. The measure is written without the bar above it, so AB would equal a number. The length of a segment always includes a unit, such as meters or inch, centimeters, feet, miles, whatever you have. So when you talk about precision, you're talking about how accurately you can measure, or exactness of the measurement that you're taking. So it depends on the smallest unit available. So for example, on a metric ruler, typically either centimeters or millimeters are your smallest unit available. So the measurement should be precise to half units of measure, and precision of a measurement in customer units is determined before reducing any fraction. So like if your measurement is 3/8, the precision would be a 1/16 of an inch. So our first example here, find the precision of each measurement. So if our first one is 5 millimeters, the precision is half that unit, or 0.5 millimeters. Notice that it's not 2.5 millimeters. It's not half the number, it's half the unit. So the unit is a millimeter, so half of a millimeter is a half, 0.5 millimeters. Here, our smallest part is a half inch, so half of an inch times a half to get half of it. So this is accurate to 1/4 of an inch, half of the half inch. So measures are real numbers, so you can do any mathematical operations you want on them. So there's this rule here, so two numbers A and B, such that A is less than N is less than B. So N is between A and B, so this reference to betweenness. So the definition in geometry of being between is that if it lies on the same line and the two parts that it divides up to add up to the total. Alright, so example 2 here. So it says find AC. Well, we know that CB is 3.3, and we know that BA is also 3.3 centimeters. So AC is equal to AB plus BC. AB is 3.3, BC is 3.3, so the whole thing is 6.6 centimeters. So for example 3, find DE. So in this case, you're looking for a piece of the whole thing. Before we start though, I'm going to turn that into decimals because I like working in decimals better. So 2 3/4 is 2.75. So we know that DF, the full thing, is equal to DE plus EF, the two parts added together. And I know what DF is. It's 12. I don't know DE, so I'm just going to leave it as DE. And I know EF is 2.75. So to solve, subtract the 2.75 from both sides. So DE is equal to, what's that going to be? 9.25, oops, sorry, off the page, inches. Alright, so example 4, this time it doesn't give you a picture, so it finds Y and QP if P is between Q and R. So we'll draw a picture. So here's a line, here's Q, here's P, here's R. So it tells you that QP is 2Y, QR, which is the full thing here, is 3Y plus 2, and PR is 21. So I set it up, the full thing, so I know that QR is equal to QP plus PR. Two parts add up to the total. So the full thing is 3Y, whoops, not plus 2, plus 1, plus 1. QP is 2Y, and PR is 21. So I'm going to move this 2Y over, so that's Y, plus 1 equals 21. Move the 1 over, Y equals 20. So that's the first part, find Y. So to find QP, I know that QP is 2 times Y, so that's 2 times 20, so that is 40. So just a definition about congruent. Two segments having the same measure are referred to as congruent. The symbol for congruent is this equal sign with the little tilde over the top. Here's a key concept, something that go in your little booklet. Accuracy measures how close you are to the actual value. You can have absolute error, which is just the raw difference between the actual and the measured, and then relative error is the percentage kind of measurement between the two. So relative error is always expressed as a percentage. So for example, 5 here, you have a length of 11 inches and an allowable of 0.5 inch. So find the absolute. Well, the absolute is the absolute of the actual measurement, and then the allowable one would be that, so it would be 0.5. The allowable is the absolute here. Relative error is the absolute error divided by the actual measure. So in this case, that would be 0.5 divided by 11, and then times 100 because it's a percentage. So which works out to be about 4.5% or so. Okay. Significant digits are also sometimes used to represent accuracy. So here are the rules of things that are significant. Non-zero digits, so anything that 1, 2, 3, 4, 5, 6, 7, 8, 9 counts. In a whole number, zeros count if they're between two non-zero numbers. Decimal numbers greater than or equal to 1, every digit is significant. And decimal numbers less than 1, the first non-zero digit and every digit to its right are significant. So we'll use those rules here to do our last example. So how many significant digits are in the following? So 35, so the rule is any non-zero digit. So for 10, zeros are only significant if they fall between whole numbers, so this 0 doesn't count, so this says only 1. But by the same rule, this 0 counts because it's between 2, so there are 3 digits there. So in decimal numbers greater than or equal to 1, which this is an example of every digit. So for this last one, non-zero digits only count for decimals less than 1 if they're to the right of the first significant digit. So this 2 counts, so every digit to the right of it counts. So this one has 3 significant digits. And that's the end of the last example, I believe. Yep.